final exercise about differential calculus, more precisely speaking, about simple or regular differential calculus using one independent variable. Here we have two examples of terms of functions where we are looking for the equation of the corresponding tangent lines at a certain position, at certain given points in the plane. So this is, you could say, sort of a classical standard setting. Now the functions are relatively interesting by themselves. The first one is obviously the reciprocal of the arctangent of x. The other one has something to do, has some resemblance with the famous Gaussian standard normal distribution, which is important in the area of statistics, as you know. So these are quite interesting terms, but this is, to be honest, there's no real application inside. It's just an exercise to get familiar once more with all the differentiation techniques, and also with this question of putting up the tangent equation. Anyway, now let's do it quickly. The first one, they both are called f of x. Please don't care. I just call them f of x, whatever they are. So f of x equals, now I put this 1 over arctangent of x in the form arctangent of x in parentheses power -1. You see what it is? This is negative exponent as a replacement for the reciprocal. Now this makes sense, because then I can apply our well-known differentiation rules more simply. So f prime of x equals, what is it? Take the exponent as a factor. So it's -1 times this expression, and then power of exponent reduced by 1, so to the power of -2. And then I have to still apply the chain rule by multiplying the inner derivative. Now, for your information, because this is, well, you could say this is knowledge out of the handbook, which I suppose you have seen before, so that actually, well, I can just use it without putting it down again. You might know that the derivative of the inverse tangent of x equals, this is a very nice fractional function, it equals 1 over 1 plus x squared. So this is standard knowledge, this is common sense, we just use it. So that's it. Now, putting things together, this equals negative, and then fraction line, well, transforming this exponential expression, or this, this sort of notation, back to fractional notation, we get this parenthesis term, this arctangent of x squared in the denominator, and I may use the short notation, which is arctangent squared of x, and then times the other one, which is 1 plus x squared in the denominator, but in parentheses, of course, because it's multiplied with the other one. So that's, it doesn't look so nice, but that's it. Now, point P, which should be checked perhaps to be valid, this point P may easily be inserted. So let's look. Well, if x equals 1, inserting here, we get 1 over arctangent of 1. Now you should know that the tangent of well, some basic knowledge about tangent and arctangent. We know that the tangent, sorry, I'm in a hurry, that's why I'm losing my words. So the tangent of pi fourth, which corresponds to an isosceles right triangle, by the way. The tangent of pi fourth is equal to 1. Everybody who has ever been concerned with a triangle of this sort knows why. Because if it's a right triangle and at the same time a isosceles, it means that automatically these two angles will be equal to pi over 4 due to the fact that the angle sum in any plane triangle equals pi. So it means that the sine and the cosine of this angle have the same value, and in the end it means that the tangent of over 4 must be equal to 1. That's background knowledge, okay? But at the same time, of course, this means that the arctangent of 1 then must be pi fourth, because that's the inverse function. And in the end, we see that now, what is it? Yeah, here. Inserting here, arctangent of 1 equals pi over 4, but we have the reciprocal, so 1 over pi fourth equals 4 over pi in the end, so that's why the function value equals 4 over pi at this point, so that's correct. Now, inserting, inserting the x value into the first derivative gets us f prime of 1, of course, then x equals 1, equals, look here, -1 over, and then, as we said, arctangent of 1, which is pi over 4, this quantity squared, and then times 1 plus 1 squared, so times 2. So in the end, I get pi squared over 16, then times 2, shortened, this is to be pi squared over 8, and then -1 over this expression. So I get negative, putting things, head and tails exchanged. So head over tails, how do you say? I don't know. So we get negative, the 8 gets here in the numerator, and then we get 8 over pi squared. By the way, this is, I don't know if you know it, but I like it very much. There's a very good approximation for pi squared, which I always use to make certain, well, you see, approximations. Just getting rough answers to questions if they are irrational. Now, pi squared is approximately equal to 10. This is quite high precision. I think the error inside is just 1 or 2% at maximum. So this is a very good estimation for pi squared. Also, this means that pi is, roughly speaking, equal to square root of 10. This is a good thing to know, just in case you forgot the decimal notation of pi. Anyway, so this is roughly speaking equal to -8 over 10, which would be roughly -0.8, just for your info. Doesn't matter so much. It means we have a negative slope anyway. And now I call it Tp of x, which is the tangent equation at point P of x as a linear equation. So there's, look at this one, you should know it. It's the so-called one-point form of the tangent equation. This is quite familiar, which is given as to be T of x equals, well, f of x0, or let's say x null. This is our starting value, then plus the slope at this starting value, x null, times now sort of a delta x expression, which is constructed in such a way that the variable x is taken minus the starting value x null, where my touching point P is located. So this is why it's called a one-point form, because this is the possibility to construct a linear function by using just one point and additionally the slope at this the slope of this linear function. You should know it. So that's the standard form of the tangent equation. This is what I use. F of x0, as we see here, is 4 over pi. I just take it over. And then I use the -8 over pi squared slope value times variable x minus starting value, which is, well, the x coordinate of point P, so -1, and that's it. I could simplify it to standard form, but it doesn't make sense with these irrational coefficients. So let's just leave it alone. I could even put 4 over pi outside, outside of another parenthesis pair. Let's leave it away. Okay, so the second one, just shortly. So this is the expression, and also here it makes sense to test whether point Q is really on this function. But that's easy, because you see, inserting 1 for x, we get 1 minus 1. This factor gets 0, and the exponential can't get 0 anyway, so we don't care. So we have 0, and then plus 1, so it's 1. That's okay. But now let's take the derivative also of this term. Well, using the product rule and then also the chain rule even. Look, this +1 is just a vertical shift. It doesn't matter at all for the first derivative, right? So f prime of x this time will be first factor differentiated gets us 1. So the second factor remains e power negative, well, parentheses x minus 1 squared over 2. That's it, the first part of the product rule. Plus, now this time the first term, take it over, which is x minus 1 parentheses, times now this one differentiated due to the chain rule, which means since it's an exponential, we get exponential of its argument unchanged, outer derivative, times inner derivative, where the inner derivative, well, you might see it, I hope you see it easily, it's negative 2 times this parentheses term x minus 1 over 2, and 2 times over 2 can be crossed out, so I get negative x minus 1, still parentheses at the moment. Actually, or interestingly, exponential terms always remain unchanged, so I can put this outside of some more brackets. I take this exponential term outside, I get it once, here it is, so I put 1 inside the brackets, the square brackets here, and I get it another minus this one, this expression times. Okay, you know what I mean? The same exponential times negative parentheses x minus 1, which but as you see from our product rule result, we have the same factor of x minus 1 again here, underlined in blue. So it's this one squared. And that's the correct transformation of this whole expression. Of course, I can resolve this to be, again, second binomial formula, x squared minus 2x plus 1. Then I can I? No, I cannot cross out this one. Instead, I can put it together. So I get x squared minus 2x plus, let me see, plus 2 it would be. And I'm not quite sure whether I made the correct transformation. Ah, sorry. Of course, this one is what I say, but here's a minus sign before. So actually, the 1 minus 1 gets away. And then this one, what we get is a negative x squared and a positive 2x. Sorry. So all that remains from this squared bracket term will be negative x squared plus 2x. And this can be transformed to be negative x times, parentheses, another x plus, and then carefully, minus 2. Now that's a bad idea perhaps, but as you see, I'm sorry for that transformation. Let me do it again. I could exchange it. It's 2x minus x squared, and now this time I can put x outside and it remains to be 2 minus x. So that's really, it's really the nicest or the most compact way of writing it down, and that's why I put it in this form in the end. So sorry for this complicated transformation here, but we want to have nice expressions after all. Sorry. Yeah. And now finally, we may just insert our point q into the first derivative, where f prime of 1 then equals, look here, this expression, inserting x equals 1 here, we get e power negative, well, 0 squared over 2, so that's exponent 0. We get e power 0, and then times x equals 1 times 1 times 2 minus 1, so 1 times 1 actually, and 1 times 1 times 1 is 1. It stays with 1. And the tangent equation, therefore, will be 1 for the f of x null, because our point q has the coordinates 1, 1, plus the slope, which is 1, times x minus, again, here, x null, so x minus 1. In the end, it's 1 plus x minus 1, so x remains, and since now the function, well, t index q of x, the tangent equation equals x, it's identical with the first bisector, simply. And now if you look at the graphs in the end, here you see it, that's the first bisector as a tangent on this modified Gaussian curve, which is quite interesting by itself. And what you see here, this is the first one, this 1/, arctangent of x function, where the point with coordinates 1 and 4/pi is the tangent point where we constructed the tangent equation. As you see here, the y-axis value is slightly above 2. Here it's 0, of course, and this is everything consistent. Look here, it was 4/pi. This is interestingly something like, what is it? I must take care. I must consider this -8/pi squared times -1 also. So putting these together, we will find something which is slightly above 2. I checked it, but not this time, right? So this is everything consistent with the plots you get with GeoGebra or other tools. Sorry for this very extended session today, but then thank you all for coming, and have a nice day. And I say now this is the well, you could say, yeah, this is the end of the playlist of Mathematics 1. As long as we won't shift contents from Math2 over to Math1 or vice versa at the moment. Now this is the finishing point. Thank you.